R1 or whatever, and then this one will be L. And this is U. This is the circuit. When we did the equation, we found almost the same thing. L didt is equal, it will be equal to U again. This is the voltage here. U minus R multiplied by x1.
R minus R0.
Right. This one is R1. So R will be R will be R1 plus R0. Right? So we will see it here. You will have the difference because of the minus will give you plus. So it will be plus there. So this is the equation that we have to use. So all what we have to do is to make y is equal to x1 plus u over r0. So OU over r0 is the current going here in this resistance. So if we define the function or the storage function as half x1 squared, if we take the derivative, v prime, it will be equal to x prime 1 multiplied by x1, which will be equal to x1 multiplied by u minus r multiplied by x1 squared. Sahih? You agree with this?
Yes.
Now from this equation, we can deduce what's the value of x1. So x1 will be equal to y minus u over r0. And then we plug it here again, so this will be y minus u over r0 multiplied by u minus r multiplied by x1 squared. And this will be equal to uy minus u squared over r0 minus r x1 squared. Everybody is okay? So if we take the integral from both sides, so this is v prime, huh? So if you take the integral, you will have the integral of y multiplied by u will be equal to v of t minus v of 0 plus r multiplied by x1 squared plus u squared over r0. So this u squared is voltage, huh? Voltage squared over r0. This is the power. Oh, sorry, there is an integral here. So this will be the integral of power, and this will be resistance times current squared also power. So this is the power dissipated at the level of the input, and this is the level of the of y at the level of the output that we have there.
The input here is y, right?
Sorry?
The input, current source, y. The current source here is y, right?
No, the current source is whatever, I. Any current.
So from this equation, y equal x1 plus u over r0 comes.
This is my output. Right? It's current, this current x1 plus the current that is going here in this resistance. This is how I define it. I define my output like this. It's like a feed forward of current.
So my input is the current, my output is the voltage on the R0.
It's current.
No, my output
Current
is
is the current going towards
this is
I0.
Is the current
It's my
that is, that is circulating here plus the current that we have inside this resistance.
Which is R.
U over R0.
But x1 plus u over r0 is equal to I. Right?
Sorry?
X1 plus u over r0 is equal to I, the input current.
Yeah.
So we got to control the source of current. This is what it will be. So all this example is just to show you the dissipation at the level of the input, because there was a question of how this happens. Right. But this is just parenthesis.
We are doing this due to find the stability of the system.
No. Just the previous example, when you started, you were not able to show the dissipation at the level of the input. I just repeated it.
But for what purpose we are doing? We are
To see
finding
the passivity,
dissipation of
the meaning of passivity. The meaning of passivity, you have the supplied energy, is equal to what is stored plus the dissipation.
And to finding the passivity is to do the purpose of finding the stability of the system.
No, because the passivity, we have seen it in the previous class. We
Yes.
used it to show the passivity, the stability of the MIT rule with the
Yes,
feed
yes.
voltage. طيب feedback linearization, this is our first class. طبعا feedback linearization is a full class in nonlinear systems. We are going to go very quickly on the major results, but the details you will see them in nonlinear class. Huh? So this is the example of systems that are nonlinear. For example, a system like the pendulum. If you look to the pendulum equation, it's a second order system. X1 prime is equal to x2, x2 equal to minus a sine of x1 plus gamma minus sine of delta minus sine of delta minus bx2 plus a constant multiplied by u, which is the force that you are applying to the pendulum. So the feedback linearization is concerned about how to have an exact linear model of this nonlinear system, right? So this is the first important point. So feedback linearization will generate a linear system. But we know from our previous knowledge that Taylor series can also generate a linear system. So Taylor series can, or Taylor approximation can generate a linear system. The difference between the two is that this is an approximation that is valid only around an equilibrium point, around an operating point. So you trim, for example, your point, you say I'm working around this pressure, 14 psi or whatever, or this altitude or this voltage. But this one will generate for you an exact linear model. So sometimes we call it, rather than call it feedback linearization, we call it exact linearization. There is no approximation there. This one is around a particular point, which means that if you are away from this point, the model it cannot be extended. The model of this point, the model of this point. The model cannot be extended. The model is no longer valid. So we cannot extrapolate the model. We cannot extend the model. It's not an extendable model. It's valid only around one point. And we are able to find how much is away using Taylor series. Right? It's Taylor series. If we stop at one particular term, the error can be quantified with the term that comes just after by looking to the maximum of this point around the domain of definition. So we are able to quantify this away, how much I can be away to declare it in the model not valid. But an example, I can have a linear model of an aircraft on the ground, right? Which is almost a car because it's 2D. But when it takes off, the model is completely different. So the model that they developed in the ground cannot be applied when I am on takeoff. However, this one is valid anywhere. Right? So this one can be extrapolated. So this one using Taylor series, this one is using feedback to make it linear. This is the difference between the two. Everybody is okay with this?
And also feedback linearization, we have all information about the system, but Taylor we lost the information for dynamo.
This is exactly the point of why it's not valid anymore. Because linearization make you lose all these information that have been about the dynamics. So this is the difference between the two. So for us, when we talk about feedback linearization, we talk about how can we make a system that is non-linear linear, but not using approximations, using an exact formula.
Professor, Yeah, what's the delta here? Stage or output?
Delta is the change of the angle. Right, you are at a certain particular point x1, so this is the angle of the pendulum. Right, so I have here the pendulum. This is x1, and you change by a value of delta. Okay, so change of the angle. Yes.
Why people sometimes use tire C, even I can see that feedback linearization is better.
This is an excellent point, but I will answer it at the end of the slide, right? I will answer this. So this is the example of nonlinear system with the pendulum. You remember, if you go back to your undergraduate, you have done linearization of this pendulum, and you assume that sine of x plus 1, sine of x1 plus delta, it's almost x plus 1 delta, right? So I assumed a very, very small angle. So basically delta does not exist. You can come here and say sine of x1 plus delta is almost 0, so delta can ignore it. It's almost 0 if x1 plus delta is 0. And then I can have it replaced by x1 only, right? If you look to Taylor series, around 0. So if I look to Taylor series of sine of theta around 0. Around 0 means theta very, very small. So this will be approximately equal to theta. So sine of 0 is 0, so 0, the first term, this is Taylor series. Second term will be cosine of theta evaluated at theta equals 0, multiplied by theta minus 0. This is the term that is linear, right? And this will give you cosine of 0 is 1 multiplied by theta. So it's almost theta. But here we would like to have something valid everywhere. So what we said, how can we take advantage of u? So I will use u to cancel all this stuff that you have here. Okay. So in particular, we are going to say so we have here, this is my integral, this is x1, this is x1 prime, which is x2, and this is another integral, this is my x2 prime. And then I'm saying that x1 prime is equal to x2, which is valid here. Then x2 prime that we have here is equal to these functions, these values of states, that I'm going to send through sine of x1 plus delta. So sine of x1 plus delta here. And then we have sine of delta. So delta, as I said, is disturbance. We can say x1 plus delta is equal to x2 if you want. It's just a disturbance in the angle. A over c is a coefficient. So we can say that over these minus multiplied by a over c. This will be equal to the value of c multiplied minus bx2. So I have to take minus bx2 also here. And then I take u multiplied by c. And this will give me the value of x2 prime. Right? So this is the implementation of this dynamic equation. So if I would like to use nonlinear term, so I'm going to say, what can I do? Here we have minus, or the plus, whatever it is that we have here, plus,
Minus A.
minus.
Why A over C? When
Minus A.
Yeah.
So this is minus here. This is also, we can put it here minus. So I can create a parallel block of the same thing, copy of this, right? So it will be sine of x1 plus delta minus sine of delta multiplied by a, and then I bring it here as plus. So if I do this, then this dynamic It's cancelled.
Just multiply C.
Okay?
Of A over C. The
No.
It has to multiply C.
It has to multiply C.
The U has to go through C.
No, it's going to be A over C is going to enter in U. It's gonna
C
enter
times
before
U
the
is
C.
here. So C times U is there. All what we have is A multiplied by this term.
They're just gonna
But
plus
for the
minus.
diagram, we can put the arrow before in the U, before the C into A over C.
No, I would like to put it like
to have the same exact equation.
this. Yeah. It doesn't matter. So all what I'm telling you is this is the idea. You are taking a block and then you are taking the nonlinear part and then you are trying to cancel it. When you cancel the nonlinear part, you will have C multiplied by U is equal to minus B multiplied by X2. This is a linear term, but you have the choice. If you would like to cancel it also, you can take it off. So you can come here and say,
plus
again, another term. B multiplied by X2, this is not minus B times X2, and I bring it here as also this. So all this block I already cancelled. So I have a direct value of C multiplied by U. And if I would like to make feedback, then all what I need to do is to take this here multiplied by minus K1 and I'm going to put over C just to make you happy. So multiplied by C, multiplied by C. Let's keep it like this. K1 and then I take X2. End of the semester. I'll bring it here, right, as the value of U. And I can take over C just to make it, take it out as a value. Everybody is okay with this? So now, the reason I made it in different colors is for a particular reason. Okay? What I wanted to show you is that this is your system. And this is your physical system, your airplane, your engine, your car, whatever you want, whatever you are trying to control. For us, it's the pendulum. All what is in red and black here
Control.
is your controller. This is the controller.
Can we say also that our controller is nonlinear?
It's exactly the question, the answer for your question. So what was your question before?
Sometimes people use tire over
Yeah.
because of nonlinear of the controller.
Because the controller is non-linear. Most of the controllers that are available outside, 95% are PID controllers, linear controllers. So they work around the operating point, one operating point, or the system is approximate bilinear. But as soon as you put a nonlinear controller, then the implementation is a process, it's more complex, the understanding is more complex. Right? So there are more challenges for this. What is the advantage?
Completely
It's
stable,
more- more
completely
linear.
linear. The system.
Huh?
The system became completely linear without
Yeah,
losing the
exactly.
dynamic.
Works for
That
every
isn't
point.
dynamic, huh?
Works for every point.
It works for every point. So the model can be extrapolated to
Just to,
any point.
we need a full observable of the system so this can work.
Not necessarily, you can put an estimator, state observer, state estimator. I mean, anything that will allow us to estimate this thing. It could be partially observable. I need only to, for example, to cancel the sign. So if this is sign of x1, I will focus on x1. And then I can take it out. So the observability is important, but it's not fully observable. It's okay. If the system is measurable or can be estimated, I can build an observer, it's okay. Is it okay what I'm trying to do? Now the other structure with that is very important for us is that the control appears exactly at the same level with the nonlinearity. Right? So what there are cases where the control does not appear at the same level of the nonlinearity. So how we are going to cancel this? Huh? So for example, this system.
Transfer to
We need to transform it in a way that will bring the nonlinearity back to
Can we integrate
the last-
Y2? Can we integrate
last
the second
state.
part and put it? Can we integrate this one and insert it in the other term?
There is a formula on how to find the transformation that can help, especially when the system is complex. And there are techniques that we can do that are straightforward. For example, this system here. So everybody understood the difference between what we do in terms of approximation and this. Your controller now is nonlinear. Huh? And you have two loops in the controller. This is very important to understand. You have the first loop, which is this one, and you have the second loop, which is this one. So the first loop is used to linearize, the second loop is used to control. So one thing that we need to pay attention to is that the inner loop has to be faster than the
outer.
outer loop. You have seen this before, cascaded controllers. The inner loop has to be always faster than the outer loop. So the same thing here. Otherwise, you will have
because we
oscillations. Because the two controllers, one is trying to do something and the other one is not settled yet. You will have issues in terms of control. So this is from practical point of view. So in my example here, y prime equal to a sine of y2 and y2 prime is equal to minus a y1 squared plus u. So in this system, the u appears with a nonlinearity, but there is another nonlinearity here where the u does not, or there is no control. There is no way to cancel it as it is right now. So how to do this? One way to do it is we are going to assume zeta 2 equal to a sine of y2, and we are going to assume that zeta 1 prime is basically equal to zeta 2. Right? Because we are putting this, all this term as zeta 2, so zeta 1 prime is equal to zeta 1. Now I need to compute zeta 2 prime. So zeta 2 prime is equal to a y2 prime multiplied by cosine of y2. Everybody is okay with this? Yes? y2 prime is given by this equation, so I'm going to be able to write it as minus y1 squared plus u multiplied by a multiplied by cosine of y2. And this will be equal to minus a times y1 squared times cosine of y2 plus u multiplied by a multiplied by cosine of. So using this transformation, I was able to move from a system where we have two linearities, one at the level of the state, one at the level of the controller, or at the same level of the controller, to have a system that is linear. Now we have, not linear, sorry, linear in one state, so zeta 1 prime is equal to zeta 2, and zeta 2 prime is equal to, I need to write everything as a function of zeta 1, zeta 2. So we know that y1 is equal to zeta 1, so this will be minus a1 minus a zeta 1 squared multiplied by cosine of y2. But cosine of y2 based on this equation, this will imply that y2 is equal to the cosine, sine inverse, or arcsine if you want, sine inverse of zeta 2 divided by a. So I'm going to write here cosine of sine inverse of zeta 2 divided by a. plus u multiplied by a multiplied by cosine of sine inverse of zeta 2 divided by a. So now I have a system that is completely described by zeta 1 and zeta 2. Yes?
Why we need to convert y1, y2 to z1, z2? Because we have u, so design u depends on u1, y1, y2.
What your controller will be a function of zeta 1 and zeta 2. What you are going to linearize is this, not this.
Yeah.
The same way.
So if you design your controller as function of y1, y2, and then you implement it here to define, to cancel the nonlinearity,
So you
your
have
controller will have zeta 1, zeta 2 plus y1 and y2 all at the same level. So in order to make it, it's a clean way to write it. You have to put everything as the same value. This is your state space. Your new state space is zeta 1, zeta 2. Yani your nonlinear system is zeta is y1, y2, but the linear is zeta 1 and zeta 2.
Is it possible for the controller to have singularities in this case?
Exactly. So the controller has singularities here. The controller is not defined everywhere. The controller is only defined in the points where the sine inverse of zeta 2 over a is different from pi over 2, multiple of pi over 2. Right? Because cosine of pi over 2 would be
0.
0.
And
Right?
inverse was 0.
Exactly. So if you would like to design a controller that makes the system linear, what you need to do is this. You need to put a controller, u. So this is my design now. Huh? This is my design of the controller. I will put u is equal to 1 over a cosine of sine inverse of zeta 2 divided by a. The whole thing multiplied by plus a1, a zeta 1 squared cosine of sine inverse of zeta 2 divided by a. So this will cancel this nonlinearity. And then I will add here minus k1 zeta 1 minus k2 zeta 2. So if I take this controller now and I plug it here,
Minus k zeta 1.
I will have zeta 1 prime is equal to zeta 2 and zeta 2 prime is equal to minus k1 zeta 1 minus k2 multiplied by zeta 2. So there are two parts in your controller. The first part takes off the nonlinearity. The second part will give you the control that you need. So this is the this is the controller. This part removes the nonlinearity, and this one is the linear controller, the usual state feedback controller.
I have a question.
Yeah.
Why when cos goes to 0, why is that a problem?
Because you are dividing by 1 over cos.
Yeah.
To go to infinity.
It will go to infinity. So, for example, if this is your drone, you don't want your drone to be taken off like this, as pi over 2. So the system here is not defined everywhere. The way to go around this is that we define this controller up to a value closer to the equilibrium point. For example, here, the way I designed it now, at the end, zeta 1 will go to 0 and zeta 2 will go to 0. Right? If the design k1 and k2 such that the system is stable, it will go to 0. So, you agree with this? There is no input. There is no reference. So the system is left to itself. And then it will have to go to 0 so the system is stable. Now, what I can do, I can say use this controller up to a certain value g star, value of the function. And then once I arrive here, then I can use linearization around this particular point. Like this, I will avoid the pi over 2 division. Everybody's okay? So two types of controls that can push me to the area, but it will work. Everybody understood what I did? I'm doing it with examples right now, no? But sometimes I'm not able to do this. Even if I have this, I'm not able to do it. So for example, I'm going to show another example here. So this one is the same as the previous one. You can do the same modification, but this one, if I look to this system, I have sine of x2 plus x2 plus 1 multiplied by x3. x2 prime is equal to x1 to the power 5 plus x3. And x1 squared plus u is equal to x prime 3. The control appears completely at the third stage. And the two first ones are nonlinear, but there is no control. And if I put zeta 1, zeta 2 like this, I will be able to do it, but
We have many
I need to reset. Huh?
Iterative process.
We can do iterative process. We will see backstepping technique later, but for now we are going to focus on feedback normalization. So how we are going to deal with the system? The way to deal with the system is by looking to the output. So I go back to my output. I have y is equal to x1. So I can say that y prime is equal to x1 prime, right? So I start from the output, not from the input, not from the states. This will be equal to sine of x2 plus plus x2 plus 1 multiplied by x3. And then in this y prime, there is no u. Still there is no u at the level of
We
y.
derive again.
So I derive again. Y double prime, it will be equal to x2 prime multiplied by sine, cosine of x2 plus x2 prime times x3 plus x2 plus 1 multiplied by x3 prime. And then I replace each one of the primes in this equation. When I replace x3 prime in this equation,
It appears.
the u will appear. Right? So I will, if I replace x3 prime here, I will not replace x2 prime, because it will take
A lot of
a lot of
space.
space. It will say that we have replaced it. Cosine of x2 plus x2 prime x3 plus x2 plus 1 multiplied by
x1
x1
Okay.
to the power 3, sir? To the power 2 plus x2 plus 1 multiplied by u. And this y double prime. So I can come here and say I will use this u to cancel all this term. And I will remove. So u, let's assume that this point here, this block is capital A. Everybody agrees with this?
Yeah.
Then I can say that my u is equal to 1 over x2 plus 1 multiplied by minus a minus k1 y prime minus k2 multiplied by y, and I plug it inside this dynamic. So I will have y double prime is equal to, at the end, minus k1 y prime minus k2.
So our new state will be y2 prime, right?
Our state will be y. Our output will be y. This is a second order equation.
So we have
So I need to add the derivative, and I need to add the derivative of order 0 and derivative of order 1. Why I need to do this? Because Ruth Hurwitz is telling me that one necessary condition is that all the coefficients should not be 0. Remember Ruth Hurwitz, huh? Yes? شفتها في الميدترم المفروض انكم رجعتوها. So Ruth Hurwitz is saying that all the parameters of the characteristic equation should not be 0. This is the necessary condition, and they should be of the same sign. So I go here and I say, since I have second derivative here, and I cancel all this term, the term that I need to add should be linear in y prime, because this will multiply s, and in the value of y. And this will go to 0, stable. And this will be my controller u that will cancel all these terms. Everybody is okay with this? But there is an issue, and this is what I would like to bring your attention to. The system that I got here is a system of two states. Second order.
We have third.
But we started with the third order. Okay.
So relative to this.
Sorry?
We have internal dynamics.
So there is an internal dynamic on the system, right? One of the state on the system that I'm not seeing. It disappeared from my linearization. So you could have this system going to zero, right? And you are very happy using MATLAB and others, while one of the state is going to the roof. Everybody's okay with this? So when we linearize and we find that the degree of the linearized system is less than the original system that we started with, we need to look to the internal dynamics and make sure that these internal dynamics under this control are stable. We are okay with this? Any questions?
How will you do that?
How?
How will we do that?
How we will do that? I will show you later what are the internal state. But these you have to look to y equal to x1. We are already seeing this, right? The value of x3 that we have there is already included here. We added with the controller. So the internal state for the system is number 2. So we need to go to number 2 under this control, right? You are measuring, you are putting the controller minus k1 minus k2 based on y, based on the feedback of x1. And then you are feedback, we are taking x2 and x3 from the system to find the controller. You go back to x2 and you check that this x2 is finite. Right? There is no other thing to do on x2. You cannot guarantee the stability of x2, but you need to be able to check it. Is it clear what I said here?
Can you repeat that?
The question of your colleague is how we can guarantee that the internal state is stable. How do we see that?
And which
We need to, since we are basically measuring x1 and x2 and x3 and we are plugging them in this equation, the state that is not appearing here is the x2 prime equal to sine of x2 plus x2 plus 1 multiplied by x3. This one we can make sure that it's stable only by monitoring. We cannot guarantee from this equation. This equation cannot guarantee that all the states are stable. The internal state has to be checked.
Maybe you can check using Lie brackets for what?
It's another stuff.
But yeah,
It's doable, but for now we look to.
yeah, but let's make questions. We can do the stability using Lie brackets. So.
The problem of the states is that you are not able to have any control of it. No? This internal state you cannot see, you cannot control. So for you have to look at something. Can we do linearization anytime we want?
No.
So this is the domain of definition of feedback linearization. So first of all, we need to look to our nonlinear system. And we have a linearization loop. This is the first loop that we have. And we have a second loop that we can use pole placement. So pole placement means that the system is controllable. So we have to look to state transformation, compute the new state, and after that look to the uncertainty in the model. Of course, they will cause an error, and this is what I would like to show you later on with adapter. So what class of knowledge system can be transformed through exact linearization to a linear system, and how to find the transformation? This is something that you would see or you have seen in nonlinear if we took nonlinear. Not every system can be linearized. So systems that are feedback linearizable, all this is blah blah blah, but I will come back to it just to finish the idea of the theorem. Here. So we jump two times. I think there is a slide that is not appearing. Yes.
Can you please explain how you're getting the equation for the U?
For the U?
Yes.
I will explain it. Just a second. This is our example. Right, so this is the condition for system that is feedback linearizable. So we said here linear system described by y prime equal to f of phi plus gy multiplied by u. So basically you have in the dynamic matrix nonlinearities, you have in the input matrix nonlinearities. F is a mapping between the state space to Rn, and the same thing for G. P is the number of input that you have here. What we are saying here is that one of the conditions is F and G should be sufficiently smooth on Y. So sufficiently smooth on Y means the derivative of these systems are smooth to a degree that we want, right? So we derive first degree, second degree, third degree, up to n minus 1, which is the degree of the system here. We are able to see, or up to n, we are able to see that the degree is smooth. Then we are saying here the system is feedback linearizable if there exists diffeomorphism. Diffeomorphism means a system that is smooth and one-to-one objective, so the function is bijective. So it's
One-to-one mapping.
one-to-one mapping, right? And this transformation has to contain the origin. The origin here represents the equilibrium point, right? It has to contain the origin because we are looking for equilibrium point at the end. Equilibrium point means the area that we are trying to do. And this transformation can transform. X is a new variable. It's not the same X that I'm using here. Huh? The system is described by Y. This is a state space. X is a new variable like zeta that I used here. So there is a zeta if you want, which is equal to the transformation of Y such that zeta can be written as zeta prime is equal to x prime equal to a times x plus b multiplied by b inverse multiplied by x multiplied by u minus delta x. Right? So all the question will be how to find alpha and how to find beta. This is what we are trying to do. How to find alpha and beta. And how to find alpha and beta, it is basically the how to select u. Your question. So for our example, if I go back to this example here, all this term is nonlinear. There is x2 prime, which is equal to sine of x2 plus 1 multiplied by x3. No, this is x1 prime. x2 prime is somewhere else there. That I have to replace here. x2 prime again in this value multiplied by x3. And then you have x2 plus 1 multiplied by x1 squared. All these are nonlinear terms. Right? So this is f of y in the theorem, right? And then you have x2 plus 1 multiplied by u. This is g of y, g of all these states that you have. So how to select u? You select u such that you take off all these nonlinearities that are appearing at the same level of u. So I took u, I call this maybe using a color. I call all this term A, right? And then I said u. If I divide by 1 over x2 plus 1, this term will go. And then we will have here a plus u, or whatever the new u. So I put minus a. And then I added the linear terms here. How did I add the linear terms? This term and this term, by looking to the dynamic that I have here, second order. So if I would like to write it completely, I will write it, for example, y double dot equal to v. And for the system to be stable, this v has to contain the first derivative and the derivative of order 0. Why? Because if I take the Laplace transform of this implies that the character, I'm not going to write this here. I will start doing the same that we are doing with the midterm, by the way. You're giving me a hard time to find the results. So all the errors go here, go here, go here. So I'm doing the same here, so sorry for that. You are following what I'm doing here, sir? So we are able to write y double dot plus k multiplied by y prime plus k2 multiplied by y equal to 0. The characteristic equation of this is s squared plus k1 multiplied by s plus k2. So according to Rutherford, this polynomial has to have all coefficients non-zero and all the same sign to be stable. For the second order is necessary and sufficient. High order is necessary only, and then we have to make the root stable. If I remove this term, the system is marginally stable. If I remove this term, the system is going to infinity because we have an integrator at the end.
It will be unstable.
It's not unstable, but it goes to infinity, so it's like unstable. It depends on the input. So if your input is an impulse, it will be stable. But if your input is 1 over s, which is doubling the zero at the pole at 0, then it will go to infinity. Okay? So it depends on the input. So this is why I'm saying it goes to infinity. Yes.
For this new system, what are the states in this case?
Why? Why the system here we will have y1 is equal to y2 and y2 prime
It's equal to this.
is equal to minus k1 multiplied by y2 minus k2 multiplied by y1.
And we always need to check the dynamic that we lose, because we had
Right, dynamic that we have lost here, because we have a second order system, not third order system. So we need to go back and check that the dynamic that we lost in this linearization is stable.
How do we know which dynamic we lost?
Yeah.
This is a very good question. How do we know? This is something that you will see. I'm talking about this here in the slides somewhere after the transformation, but you need to see the order of derivatives that you have, and you need to see which one are impacted by the controller. Okay, so for example, here we have u directly at the level of x3. We have x1 to the power 3, x1 also available in the controller. Both of them are controlled, but x2 is not there. So we are going to say x2 could be the variable that we lost.
Can you repeat it? Just the last one.
We have in this example, we have u at the level of x3. Right, so this controller will act on the value of x3. We have the x1 at the level of x3, so both of them will be active, but x2 is not here.
So x2 will be the internal state.
So x2 will be the internal state. Yeah, the rule of
Okay,
thumb.
and we need to see which is touching you.
What is the controller?
Because you is a level x3, but it's acting with x1. So they are acting.
Exactly.
And so
X2 is
if you appear at the fourth differentiation, or
If you what?
if you appears at the differentiation of the fourth,
If you what?
if you
If you appears at
appears at the fourth differentiation,
for differentiation.
then what
Cannot be.
It cannot be.
For the system, it cannot be.
For any other system,
Another system is that the system is at least fourth order.
So it means that if the u does not appear at the maximum differentiation of the equation, then it cannot be linearized by the system.
No, it cannot be. It cannot be that for this system, for example, suppose that we have this system, this state, and we keep deriving, and u does not appear. It does not. It does not. There is no u. You understand what I'm saying? It cannot happen. So u will appear either before the degree of the system, and the degree n minus I, مثلا, 1 or 2 or whatever, but it has to appear when you arrive to n at the highest. Yes.
For example, if you have plus x2 in the x prime x3 dot, so x1 and x2 appears in the third state. In that case, can we say that we don't need to look for the internal state?
No, we need to look to the internal state, but
both x1 and x2 appear.
exactly. But we need to see which one now is affected. We need to investigate more. Here, but I told you here is just a rule of thumb. Basically, what will be the state that I'm going to see. But normally you should investigate carefully which one you are losing. So if x2 is in x3 prime, it means either x2 or x1 that you are losing basically in the controller.
So we need to dig more for this.
Yes. x1 it cannot be in general because this is your output. So if you say y goes to 0, it means that x1 is going to 0. So, because we said y is equal to x1.
Okay.
Right? x3 is on the level of the controller, so x2 will be always affected.
So probably it will be x2.
There's no fixed rule.
There's no fixed rule. You need to investigate more which state has been lost. In the so the notion of internal state is very important to keep in mind. All right. So there are several ways to do this. Adaptive control. Sorry, not adaptive control, but feedback realization. There is a way to find the transformation, but it requires a lot of mathematics and partial derivatives. So basically what we have to solve is a set of partial derivatives like this to be able to find this transformation that will transform a system of order n from nonlinear to linear. Okay. In the slide there is an example that shows you how to do this. So we have partial derivatives that will involve f of y. You remember y prime is equal to f of y plus g of y multiplied by u. So there are partial differential equations that will involve f of y, but also there are partial equations that will involve g. So g will be almost equal to 0 based on the fact that I'm assuming that my transformation or the transformation that I'm using will lead to a system that is canonical. So I'm assuming that the A matrix here is canonical for this canonical form. So if you assume this A matrix and you assume this D matrix as your value of linearization of the system, these are the partial differential equations that we are going to have to solve. You have to find a solution for this. So not every system is linearizable, right? And sometimes systems, it's not evident how we are going to linearize it, right? So again, as I told you before, feedback linearization is just a tool. We look to the feedback realization. Can we apply? If we can, we could. There are some advantages, as I told you. It can make the system the exact linearization of the system, so we don't need approximation. But the cost of this is more nonlinear controller and a two-loop control system. So there's a disadvantage. The real system might be different from normal system. This one I will show you today how to deal with it. In the sliding mode control is almost the same thing as feedback linearization, but assuming the worst case of the difference between the systems. So we'll see this later in the sliding mode. But for this system here, we are saying that the system can be complex. It's the system can have nonlinear controller, two cascaded controllers, but it's maybe better than going and making linearization over 20 points or 1,000 points. Everybody's okay with this? Yes? في شيء غامض على الفيدباك linearization؟ طبعا it's just we are not covering it fully in terms of theory, but it's just to introduce for us how to make it adaptive. All right, so let's progress a little bit here. I'm going to give you all the answers so you can try to find all the answers if you have some answers about some of the problems that you are looking at. Here we go. So these are for the internal states that we are looking at, so you can see which state are changed. Let's go back here. All right, so we have here two systems. And I would like you to work with me on these two systems. The first system is derivative of x1 with respect to xt dxt dt is equal to x2 plus f of x1. And dx2 is equal to u, and I would like this system to be linearized. Can you do that? Take a piece of paper and do it, and then we have another system we do it later.
If x1 is nonlinear,
F of x1 is nonlinear. Nonlinear functions, yes. Do that and let's work on it together, because this I will use it as a way to go to adaptive. And what we are going to do for feedback realization and adaptive can also apply to neural network. So if we have an approximation of neural network with this function of effects, we can do exactly the same thing. I will show you later how to do it. I think what I'm doing right now, it's going to allow you to do the adaptive on feedback realization, but it will not give you the full mastery of feedback realization. We'll do it in our linear course, inshallah. So we can use exactly the same thing that we did before, sir?
Yeah.
Let's give time to our friends finish.
Theta here, it's just constant or what?
Theta is the second problem, is a constant.
Constant, yeah.
Yes. Vector.
Depends the
Could be a
time.
vector. Huh?
Yeah, right, but it's not depends on the time. Theta.
Theta are constant values. It depends on time if we are going to make it adaptive, but we are going to say that it varies very slowly, theta,
Yeah.
compared to ours.
Sorry, Professor, it's two different questions on the same question.
Sorry?
The same question on two different questions.
Two different questions. For now, two different questions. Are we done with this? Yes?
The first one.
So we can do the same. We can say zeta 1 will be equal to x1, and zeta 2 will be equal to zeta 1 prime, which is equal to x2 plus f of x. Right? Then zeta 2 prime, it will be equal to x2 prime plus
x1 prime f
x1 prime
dash x1.
derivative of f of x1 with respect to x1, like what we did with the sine and cosine. Right?
Just is if x1 dot, how we can go x1 dot
Fine.
I didn't get this this one. Why x1 dot derivative with the fx?
So if you have cosine of x1, sine of x1 that we did before, huh? and you took the derivative of this with respect to time. Time, not x1.
Yeah, I knew.
So what
x1
would,
dot
so this would be equal to chain rule x1 prime.
df dx dx is a function of process.
خلاص?
Alright.
You are not convinced?
No, I get it.
Okay. So on the slide there is a dot here, but there is a dash here. Huh? Showing that there is derivative of f with respect to x1. So if I replace this by u, this will be equal to what? X2 prime equal to u, we said, huh? So u plus x1 prime. x1 prime is equal to x2 plus f of x. Multiplied by derivative of f of x1 with respect to x1. So this x2 plus f of x is our zeta1, zeta2 that we have here. Okay. So if I look to my controller will have to have two components, component 1 and component 2. So the component 1 will be minus x2 plus f of x multiplied by derivative of f with respect to x1 minus k1 zeta 1 minus k2 zeta 2. So my controller assumes that f is known and definitely derivative of f is also known. So f and derivative of f are both known. Otherwise the controller will be invisible. Cannot put if we cannot realize it.
Or we can use the error.
Which one?
Error, like if we try to use random fx and compare it to the something like we did.
We will
with
not say random, but we say initial value.
No, yes,
and
initial.
then we update.
Yes, like we did with
This
Ahmed.
is adaptive.
Yes, like that.
Right. Everybody is okay with this? So one way to do this, or the intermediate way, is to assume that f of x is not known, but f of x can be written as theta multiplied by a function, we can call it w of x. W of x is known, but theta is not known. Everybody is okay with this? All right, so let's redo it again. Assuming this, we are going to do the second example, but now we are going to assume theta is not known, but f is known. Okay with this?
Yeah.
All right, let's do
Theta
that.
is constant.
Huh?
Theta is constant.
Theta is a parameter that can change with time, right? So theta, because therefore we are deriving the whole thing with respect to x1, but theta now we are introducing it as a parameter. So maybe don't use w because later on we say phi of x, huh? Because later on maybe you'll be confused with the w that we're going to use. So let's assume that we have this. So basically we are in the second case. You agree with this?
Is there a specific way we choose our phi? Like, because I mean, you mentioned stuff that f of x we assume we don't know it, then we assume that it's equal to phi of x, which is known multiplied by new parameter theta. So is there a way we choose our phi?
If you use neural network, phi of x would be all the activation function in neural network. If you use a specific function, you say my function is in fact multiple of sine and cosine. Fourier series, for example, theta 1 times sine of x plus theta 2 sine of 2x plus theta 3 times sine of 3x. all the sign effects are known, but I don't know the amplitudes. Theta 1, theta 2, theta 3.
But then in case of Fourier series, then you would need like an infinite.
No.
But you can stop at a certain level. It's an approximation of f. يلا شباب وين وصلنا؟ You have done the second example? Not yet. Alright, you are done? Yes? So what will be the second derivative of zeta 2 prime? It will be equal to x2 prime again, and we x2 prime we know it's equal to u. We will use the x2 prime. X2 prime plus theta prime, not theta,
D of f.
f of x plus theta x1 prime df dx1. Huh?
Yes.
So again, this will be equal to u plus theta prime of x plus theta multiplied by x1 prime df dx1 multiplied by evaluate at x1 and derivative with respect to x1. So what it is.
Do you not say that theta point would be 0 because it's too slow?
Yeah, too slow, but it varies with respect to time. It's not constant. Your friend is saying, is it variable with respect to time? So I'm trying to avoid to tell you that this is time variant system. So theta changes, not very slow. Okay, because if I tell you theta changes with respect to time, it becomes theta time variant system, and it's another beast. So the new u will be minus all this, huh? But this means
You don't know.
we don't know theta.
So theta hat.
So we have theta hat, and we need to find theta prime, right? We could be that we don't know also f,
F.
right? It could be that all these terms are not known. So at the time, this controller u will not be visible. Everybody agrees with that? So now how to get out of the impasse of all this? How to do it? So the way we do it, we are going to say that, for example, for this particular system, can I erase this?
It's my suggestion. I suggest not. I think it's not.
This is theta hat prime, theta hat. It's an estimate of theta. We don't know theta, huh?
Yes.
So we are going to say that zeta 2 is my variable. I'm going to use it in my system. Right? So there are variables that are on the system, and there are variables that I'm creating. The variables that are in the system are x1, x2, what I'm creating is zeta 1 and zeta 2. So zeta 2 is going to be equal to x2 plus theta hat multiplied by f of x. Theta hat is an estimate of theta. Then we go back to our system. We have zeta 1 prime, which is equal to zeta 2. Zeta 1 prime in my system, it's equal to x2 plus theta hat multiplied by plus theta multiplied by f of x. So zeta 1 prime, according to my new notation, it's not equal to zeta, to zeta 1 prime. So zeta 1 prime is not equal to zeta 2.
Yeah, we have to.
So what I'm going to do is I'm going to remove theta hat of f of x and add theta hat of f of x. Here. We are okay with this? So from here I can get
Zeta
x2 plus theta hat f of x, which is zeta 2
or zeta 2
plus theta minus theta hat multiplied by
x.
and this is the error in parameters. And this value is zeta 2. Everybody's okay with this? Now if I go back to derivative of zeta 2 prime, so let's finalize zeta 1. Zeta 1 prime will be equal to zeta 2 plus theta 10, which is theta minus theta hat, the whole thing multiplied by f of x. And here we will have zeta 2 prime. Zeta 2 prime will be, zeta 2 prime, this is zeta 2, huh? Okay. It will be equal to x2 prime plus theta hat prime, right? Theta hat prime is here, multiplied by f of x, plus theta hat multiplied by the derivative of f with respect to x prime. And the derivative of x2 prime is equal to u. So u will be plus
I think we're missing x1 dot.
this one here.
No, the last one. The differential is already with respect to time.
Ah, yes. That's x1 prime.
Not
Yeah,
dot.
multiplied by the
Something like
so this x2 and x1 are from the system, not from me. Right? So this x2 prime will be replaced by u. This will be theta hat prime multiplied by f of x1 plus theta hat multiplied by derivative of f with respect to x1 multiplied by x2 plus theta f of x, not theta hat. Huh? You agree with that? That is theta, not theta hat? Yes, because this x1 prime is coming from the system. So if I take a nonlinear control system that will remove all these, right? With adding here minus theta hat and plus theta hat again, so theta hat 10, I will have, if we go back here, zeta 1 prime is equal to zeta 2 plus theta hat multiplied by f of x1, and zeta 2 prime is equal to u plus theta hat prime f of x1 plus theta hat multiplied by derivative of f of x1 multiplied by x2 plus theta f of x minus theta hat f of x plus theta hat f of x. So I will have theta hat, theta tilde appearing here in the equation of my system. And I will have theta hat also appearing in this equation here. So the system will have two variables now, zeta 1, zeta 2, but in addition to have theta tilde that we have here, it will appear in the dynamic. And the fact that I'm going to use this controller to stabilize the system will not guarantee the stability. Right? Even if I use U to cancel all this nonlinear term, it will remove all these terms except
Yeah.
theta tilde f of x. It will stay. You cannot remove it.
Because I didn't.
Right, so it will stay in this equation at the top. There's a plus here. So there, the theta tilde will appear in the numerator and the zeta 1 prime, and it will appear in zeta 2 prime. I will be able to use U to cancel this term, but I cannot cancel the theta tilde that is here, equal to 2, because I don't know
I didn't know.
theta.
Yeah.
Right, so this term will appear also in the second equation. So your system has now two equations, dynamic of zeta 1, zeta 2, but they are affected with the error between theta and theta. What is it?
The last state you said.
This term you cannot take out, huh? What is it here? This is theta. This theta you don't know. Theta minus theta tilde is equal to the tilde. Theta hat minus theta hat is theta tilde. So this term you cannot be removed, it has to stay there. But I'm able to remove this term, and I'm able to remove this term, and I'm able to remove this term. If I replace U by a linear system, I will have zeta 1 prime equal to zeta 2 plus theta tilde f of x1, right? And then we can try to find how to represent f of x1 here in terms of zeta. And zeta 2 prime, it will be equal to minus k1 multiplied by zeta 1 minus k2 zeta 2. But this term will stay here, right? So plus theta tilde multiplied by f of x multiplied by theta hat multiplied by the derivative of f with respect to x1. So this is how your system will appear. Everybody agrees with this? So this system is a second order system. And in order to guarantee the stability now, we have no choice only by going through Lyapunov. So in order to do this in Lyapunov, I'm going to reduce the system. I'm going to give you another example of first order system, and then I will go to the next slide which had the system in full states.
Okay.
All right? So let's take an example of first order system. Suppose I have y prime is equal to minus a times y plus theta multiplied by f of y plus u. Very simple system. All right? Single system, single order. To linearize this system, u has to be equal to minus theta multiplied by f of y. If I'm not happy with the value of minus a times y, I need to change it. Then I can add minus k1 multiplied by y. K1 will be affecting the value of a
Yeah.
to have the dynamic that I want.
You can control it.
Right? But since I don't know the value of theta, u can be only done based on
Yeah, sure.
theta theta. Everybody is okay with this?
Mm.
So y prime then will be equal to minus a plus k1 multiplied by y
Yes.
plus
F of
delta times f of y
theta t.
minus theta hat multiplied by f of y. So your dynamic equation is equal to minus a plus k1 times y plus theta tilde multiplied by f of y. Theta tilde for us is equal to
Y minus.
theta minus theta. Everybody agrees with that?
Yes.
So this is exactly what we got there, except that this is dimension 2 state space model, but this one is one equation.
Let's use your economic function.
Now, can I say that the system is stable?
No.
No.
Even if this term is positive, a plus k1 is positive, and y prime is equal to minus a times y alone is stable.
Theta
Because of this presence, I cannot say it's stable. This is a continuous drift that is function of y, it can make it completely unstable. Alright? So what I will do, I will put the Lyapunov function v, and I will say v will be equal to half
One.
multiplied by y squared plus 1 over 2 gamma multiplied by theta tilde squared. So in order for me to do stability, I will have to define a Lyapunov function that takes care of my states, and it takes care about the error of parameters that we have here. Up to now, everything is clear? Are you okay with this? So in order to guarantee that this is a function that is positive, it's 0 only when y is equal to 0, so we'll have to converge to 0, y equal to 0 and theta tilde equal to 0. So we are supposed to converge to y0 and theta tilde. Here the desired value of y is 0. I want to bring to the equilibrium, 0. I will redo the example here with if what we want is not 0, what will happen? Correct? But for now it's 0, so we are going to 0, 0 with this function. If the derivative of this function is negative. So we take the derivative, and this derivative will give me y prime multiplied by y plus 1 over gamma theta tilde prime times theta. You are okay with this? You are clear with this? So we replace this y prime by its value, so we are going to say this is minus a plus k1 multiplied by y squared, so y times y, plus theta tilde times f of y multiplied by y, right? So y multiplied by y prime, so this is y prime here, theta tilde, plus 1 over gamma theta tilde prime multiplied by theta tilde. What's my objective?
Find theta
This
delta
is negative.
to create v dot. It's less than 0.
We would like to create v dot less than 0. Ah, this is our target. What control we have here?
Theta delta.
Theta
Theta hat.
theta hat dot, which is theta tilde dot, right? Because we are
Because
going to assume
theta delta.
yeah, theta tilde. So we are going to select theta tilde dot to make sure that this is 0, because we have the control in it. And if we make this one 0, then we will have v prime equal to minus
It's negative.
a
It's negative.
times y squared, which is negative all the time, and it's 0 only at 0. So making the derivative, this term equal to 0 means we have theta tilde multiplied by f of y multiplied by y plus theta tilde prime equal to 0. So theta tilde will be equal to there's gamma here somewhere, so this one going gamma. So theta tilde will be equal to minus gamma multiplied by f of y multiplied by y. What is this?
Delta.
The
Delta.
one that you use
To create a state.
to make it simple.
So what did we call this? What did we call this last time?
Adaptation.
Adaptation rule, not MIT rule. Adaptation rule. Adaptation rule. So this represents the adaptation rule, or how we are going to update the value of theta. The controller is function of theta hat. We said that theta changes, but it's slow to change. So we are going to assume theta tilde prime, which is equal to theta prime minus theta hat prime, almost the same as minus theta hat prime, which is equal to minus gamma f of y multiplied by y. So this will imply that theta hat prime equal to gamma f of y multiplied by y. So this is how I'm going to update my estimate of theta hat inside the controller. Everybody is okay with this? Yes? So what will happen if we don't have our objective 0? So again, I'm going to start with the same example. It's a simple example, but it shows all the idea behind it. So we have y prime is equal to minus a multiplied by y plus theta multiplied by f of y. This is our system. And my objective is to have y equal to y desired.
There is no controller in here.
Plus use, huh? This is our system for the beginning. So our objective is to have y equal to y desired. So what we will do, we look to this and we try to basically change the dynamic. How we are going to change the dynamic? By expressing the error dynamic. The error dynamic. And the error dynamic, the variable or the error is equal to y minus y desired. This is what we want. So I will come to this system. This is my original system, minus a multiplied by y plus theta f of y plus u. I will subtract y desired prime from here, y minus y desired prime. So this will be equal to minus a times y, and I'm going to add here plus a y desired minus a y desired, so it's like I'm given 0. I added here minus y desired prime, so I'm going to put minus y desired prime here, so that they can cancel between the two.
Yes.
And then I will add plus theta f of y multiplied by plus u.
Okay.
Everybody agrees with this?
Yes.
So I will have then e prime, this is my e prime, is equal to minus a times y minus yd, which is e. So this term will give me the value of minus a times e, minus a times y desired, minus y desired prime, plus theta f of y, plus u. So in order to obtain the dynamic going to 0 the way I want, I'm going to select u equal to a multiplied by y desired, so I can cancel this step. And it's known, I know y desired, right?
It's
I know.
one.
Plus y desired prime also is known, I just have to take the derivative of y desired, minus theta multiplied by f of y, right? And
We
then
don't know theta.
You don't have to.
I will come back to theta.
Okay.
Don't estimate.
So this will cancel all these terms, but maybe I'm not happy with minus a times e. I would like the error to go differently,
Okay, we add
dynamic,
plus
so we can
K1.
add minus k1 multiplied by e, just to be able to affect
To go faster.
faster, slower, whatever we want. Huh? I don't know the value of theta, so I'll put theta hat here. Everybody's okay? Then I replace everything in the dynamic equation again. So I will have e prime, it will be equal to minus a plus k1, the whole thing multiplied by e. The y, a times y desired will cancel this. Y dd prime will cancel this, plus theta tilde f of y.
What is theta?
Minus K1.
So theta minus theta tilde is theta tilde.
Okay.
Theta tilde times f of y. And this system is now the system that I need to look at in order to make sure that e goes to
0.
0. So what should I do?
Level.
Lyapunov. Go back to Lyapunov. Right? Because this is a nonlinear term, unknown. Lyapunov. V equal to half e squared plus 1 over gamma theta tilde squared. And I find the dynamic of the equation that I want. So Make sense?
Yes.
Now this theta could be what we found here. We found how we are going to update theta hat. So the adaptation rule of theta. We can do exactly the same thing with neural network. Neural network is weights times function that are known. So we can follow exactly the same steps, and what we are going to get is how we are going to adapt the neural network gains in order to have the controller feasible. So it would be, if you want neuroadaptive-based controller. Okay. But you need to use the 5 functions, which are the activation function that you have in neural network. Is it clear what I said? Make sense? Clear? So the process is exactly the same, except that it becomes a little bit more complicated when you go to 2 states. And this is why I did not want to jump here. Right? So when you go to 2 states, it's exactly the same thing. We go one by one, and then we replace the dash here that you have is the derivative of f with respect to x1. Then you have to write it in matrix form. So you have here f of zeta 1, theta hat, f of zeta 1, f prime of zeta 1 times theta tilde plus 0, 1, v. V is your linear system, your linear controller or linear part. And then rather than having y desired, now you have a reference model. So we want this dynamic to follow this desired model. This desired model has the same error dynamic, so we did not make it different, but we can make it different by adding minus k times the state. So we can manipulate this A2, A1. For example, suppose that here we have 1, 2, here we have 3, 4. So we need to come to our controller and we add a component that has 0, 0 numerator. So denominator will be minus k1 minus k2 multiplied by the state, right? That we will add to our. All right, so you when you build the dynamic of the error, what you are going to get is a matrix that is known. This matrix is known. So in our case, our matrix is known is A plus K1. Right? In this case here, it's minus A2 minus A1. And then you will have another term that is function of theta tilde. Right? So we are going to say there is a B equivalent of B matrix, which is f of zeta 1 and theta hat f of zeta 1 and zeta hat prime. This term can be computed because we know f, we know zeta 1. So this term B is known, multiplied by theta tilde. So it's exactly the same thing that we found here. But this is a single equation, single order, and this one is second order. So what will be the next step? Lyapunov. So we put the Lyapunov function. So V is equal to E squared PE plus 1 over gamma theta tilde squared. We take the derivative, this will give us this kind of form, right? Because it's a multi-dimensional system, so high order system. And from here we are going to try to find what should be the update rate for theta hat that will remove all these terms that we have inside. Why you have a plus here? Why you have plus gamma multiplied by B transpose PE?
Because we have theta delta equal theta, not minus theta.
Exactly, because we have theta minus theta hat. In fact, the derivative theta tilde,
It's theta hat.
theta tilde from here is equal to minus B transpose P multiplied by E. But since we are interested in theta hat in the controller, so the derivative of theta hat will have a minus multiplied by minus. So this is why I have a plus theta tilde here.
If theta delta it's matrix, not singular.
Which one?
Theta delta square. It's not.
It's not one parameter.
Yeah, it's
Then it
for example,
becomes
matrix or diagonal matrix.
it becomes theta tilde transpose times theta tilde.
Yeah, so we need
Same thing.
see.
Same thing. We have to do. The advantage of this is that B transpose P multiplied by E that you are seeing here is a scalar value.
Scalar value.
So if it's a
All
scalar
all scalar value.
or scalar value. So since it's scalar value, this is a vector theta tilde, then the derivative of this is also it's the gradient,
The gradient.
right? So we are able to find the value of each derivative there. But we need to have transpose appearing in the equation. Okay? Any question about what I did with you here? So let's summarize it. We are going to, in fact, we are not going to close feedback linearization because when we go to backstepping is feedback linearization but iterative. Both iteration by iteration. So we will see it again. Okay? But the way we are talking about here, first of all, we have to identify the nonlinearity in the system. So this is our nonlinearity. We have two options to deal with this. Either we transform the state space in another state space that is that has the nonlinearity at the level of the input. Everything else is linear. Or we go to the output and we keep deriving the output until we have an input-output relationship between you and the output where the nonlinearity appears there. And then we try to make the constellation. If there is any parameter that is unknown, the controller cannot be a function of this unknown. It has to be a function of its estimate. And when we put an estimate, then there will be a term that will appear, which is the difference between the real value and the estimate that you are using in the controller. And this error will affect your control system. How to go with this? Everything else is mathematical representation and how to manipulate this. But normally you are going to have a dynamic of error. This is the dynamic of the error, where you have the desired dynamic plus a term that you would like to take it off, right? To make it equal to 0. This term, in order to make it equal to 0 and guarantee the stability, we use our friend Lyapunov. We define a function v, which is equal to E transpose P E plus 1 over gamma theta tilde parameter squared, or theta tilde times theta tilde. Theta tilde transpose times theta tilde. Sometimes we are not even happy with theta tilde transpose times theta tilde. We think that some parameters are more important than others. So we will put theta tilde transpose W times theta tilde. So we introduce a matrix in between, just to be able to differentiate between the weights. The 1 over gamma that you have there could be not uniform, so we can have theta tilde transpose. Right? If we have a system that is multivariable, I can point to this theta tilde. And you can make it as complicated as we want. Huh? Theta tilde transpose multiplied by 1 over gamma 1, 1 over gamma 2, 1 over gamma 3, whatever it is. So each one of my parameters has a different weight. Right? Each. So I can say, for example, the most important parameter for me is the error between theta 2 and theta 1. And theta 2 and the error theta 2 minus theta 2 half. The rest I can make an error, but it's not really important. Right? So what I need to do, I need to make sure that 1 over gamma 2 is the highest between all these three. So I will put gamma 2 the smallest possible. So to push in the controller, to minimize the controller, he has to minimize theta 2 tilde. Right? And the usual case, we can put 1 over gamma multiplied by the identity, and then we take 1 over gamma out. What I did make sense for you?
Yes.
Right. So this completes for us the feedback linearization. It cannot be applied every time. Sometimes we cannot apply it. The system is very complex to apply it. It does not fit the theorem to find the morphism that will allow me to transform it to linearizable system. Sometimes there are singularities in the controller because of the fact that I have 1 over divided by 0. And this division by 0 means there are operating points that you should not stay in. You can pass by, but you should not stay in. For example, if I have a controller where 0 is the singularity in the controller, then I will make sure that it will never stay at 0. and then I will apply the control. But if it stays at 0, the system becomes unstable, right? So this is one. Once we do the controller, we have to look to which parameter we have. The parameter that we don't have the control will be function of the estimate, and then we rewrite the equations again in order to make sure that the error between the parameter, the estimate of the parameter of the controller and the real parameter are clear in the dynamic. Once they are clear, we use Lyapunov and we try to make sure that the derivative of Lyapunov is negative. Now, once I do the Lyapunov negative, I know that this term is negative, it will be stable. Then I have the derivative of theta is equal to minus gamma b transpose p multiplied by e. So I will use gamma to make sure that this error goes faster to 0. This theta tail can go to 0 if the error is equal to 0 without conversion to the real value of theta 2. The same problem that we had before. Alright? So this term can converge to a value, especially if there are some singularities we are not closer to the equilibrium. It can converge to a value, but it's not the right value. But it guarantees stability. Does it make sense what I did with you today? Yes? Alright? I think I lost you somewhere somehow. Anything not clear? Clear. Have a nice weekend. I have nothing else to add. So what I will do with you next time is backstepping. So we will build on this and we say, what if we cannot remove the nonlinearities from the beginning? And the system has a special structure. We can see that the structure in the system repeats itself and we would like to take advantage of it. Backstepping controller is a good controller, but it's not an excellent controller. Right? So it does the job, but it's not really the best of the controllers that we have, but it still does the job for us. So we'll see how we are going to do it. Okay?
Yes.
Jazakumullah khair.